morning.
Morning, all you lovely people. I'm so excited. I'm sad that today is Friday for the conference purposes. I'm excited that today is Friday for just life purposes, right? Fridays always seem better. Although in a virtual world, I'm not sure that that stays true anymore. While we're waiting for all of our colleagues to join us this morning, I'm going to just take a quick run through the agenda. So I'm going to share my screen for a moment and tell you where we are at, what to expect for the day, and kind of our KI updates before we turn it over to Dave for a formal open with Organizer Corner or whatever you renamed it. And I can't do an Elmo voice, Dave, so sorry about that one. I'm going to stick with the Organizer Corner for now. So today is Friday. A few quick notes. Very soon, we're going to be hearing from Rob Phillips and his collaborator, Christina Hueschen. I'm sorry, I didn't have a chance to catch how to say her last name, but hopefully we'll hear more soon.
That was great.
Oh, great. Thank you. Then we'll move into those small groups and do a Q&A with our keynote, take a little break. This is our last planned scheduled social activity after lunch, so we do hope that you will join us for that. And then we're going to move into an expert panel. So we've been very fortunate to have experts join us throughout the week, and we are going to put them in a panel and let you ask them all of your interesting and engaging questions that you might have not had a chance to ask them yet in the conference. And then we're going to kind of close with the town hall with Dave and Elizabeth, our two primary organizers for this event and next year's event. And they're going to lead us in a kind of open format, open question kind of format this afternoon before we do our close and open the Wonder Room again. I'd like to thank those few people who did come to the informal networking this morning. I do hope that you're making a few connections with people. I know Jocelyn charged us with meeting at least 2 new people at this conference that we might follow up with in collaborations or conversations after this conference. I hope you take us up on that opportunity. I want to point out a couple of things just in case you missed that they were visible now. So importantly, that training and travel award information that Dave talked to us about earlier in the week, you can find that information in KaiStorm now. So you can kind of see that. Importantly, the deadline and the email address is there for you. And I'm sure Dave can answer any additional questions that you might have regarding that. And also we went ahead and moved that funding talk over onto the quick links as well, so that if you do have any follow-up questions or anything like that, you could reach out to Matthew for those thoughts as well. We have been working backwards, just a reminder with all of our presentations to answer any questions that were asked in KaiStorm that have not been addressed or were not addressed verbally in the room during the Q&A session. So as a reminder, pardon me, that is live now for our Keynote 3. So as you are listening to the presentations, please feel free to drop those questions here. And then we will go into the small group discussion, ask some additional questions, and then come back for that formal Q&A piece. I think with that, Jocelyn or Malachi, did I miss anything before we turn it over to Dave for the Organizer's Corner portion of the morning?
Nope, I think you got everything.
Awesome. So with that, Dave, the floor is yours.
Guess what Elmo's thinking about?
That I can't do or won't do. I'm not really sure which
Why
one.
biologists devalue phenomenological and theoretical models? That's right. Why biologists devalue both theoretical and phenomenological models? Okay, I wasn't going to do Elmo, but since you brought it up and it's Friday, I decided to do it. What the heck? So today I'm gonna break with tradition, not do Organizer's Corner and recap highlights from yesterday. Rather, I'm going to look ahead to today with excitement to Rob Phillips' talk, and I have to let you in on some conversations I've had with Rob recently where he went back and forth on his title and subject a bit. And I came to realize that Rob is to scientific talk titles what I am to band names. People who know me well know that I'm constantly coming up with band names like bovine retina, collateral damage. I mean, I have a list of 100. And I think that's kind of the way Rob is with scientific talk titles. Every single one of them is just an absolute hook. You just wonder, what is this going to be about? So moving on, I just want to emphasize that as Donalyn did, we have some important events today beyond Rob's talk. I encourage everyone, if you possibly can, to come to the town hall. This is going to be a 30 or 40-minute session. It's really important at the end of this meeting that we get together and talk about how this meeting went, what it could be in the future, how it can be improved, and most of all, how we can really succeed in this mission, a difficult mission, I think, of having a systems biology community and not all just go back to our corners after it. So that's what I want to talk about in the town hall. We will also distribute a short online survey, which we hope you'll take before you leave the meeting. But we will also offer you the chance to do it again next week. It will only take 5 minutes. This meeting, as you know, is free, but the small fee we charge is please do the survey. This is important information we gather. Anybody who's ever had an NSF grant knows you have to write an annual report. So the kinds of feedback we get from you is going into that report. Finally, the closing ceremonies. There will be some important announcements regarding next year's meeting. So also try to hang around for that. One last thing, the Finding Your Inner Modeler YouTube channel is up. Michael Blinoff has been working on it with Malachi's help. Malachi is the guy in the truck. He's been recording and editing all the videos. A lot of the meeting has been posted, with the exception of people who said they didn't want their talks posted. So of course we respected that. And it's not completely done, but as of right now, you can go to YouTube and search for Finding Your Inner Modeler and find a good part of this meeting already available for you when you can't sleep. That you can just rewatch these talks, and probably that will make it even harder to sleep. But anyway, it's all there for you, or will be by the end of next week. And I guess that's about all I have to say for now. I'm going to turn it over to hopefully Suzanne. Was she able to get on?
I'm here.
Okay, because yeah, you're here. Okay, Suzanne, take it away.
Okay, great. Thanks, Dave. Good morning, everybody. It's my honor to introduce Rob Phillips. He's the Fred and Nancy Morris Professor of Biophysics and Biology at Caltech. He has a BS from the University of Minnesota and a PhD from Washington University. And he's got some really intriguing things in his bio. If you haven't read it yet, you should definitely read it. I'm going to quote from one of them. Prior to the great fun of a life in science, he spent 7 years of travel, self-study, and work as an electrician. He's actually got a link to one of his interviews, and that link says, the title of that link is An Unusual Career Path Sparked by Stories About Science, and you may enjoy taking a look at that link. So Rob's lab works on a variety of topics that range from principles of allosteric signaling to the statistical physics of gene regulation and the role of mechanosensation in cellular physiology. And to quote him again, the work in his laboratory has one central aim, and that is to explore the extent to which biological phenomena can be subjected to a cycle of prediction and experiment familiar from physics. So very much aligned with the goals of this meeting. I also found it really interesting to look at his website. You might want to take a look at it. He's got this gorgeous photo of him surfing. And so I wish we were in person so we could get a beer with Rob and learn more about some of the things he does outside the lab. Co-presenting with Rob this morning is Dr. Christina Hueschen. I hope I pronounced your name correctly. I apologize if I haven't. She's a postdoc in Alex Dunn's lab at Stanford, and she studies mechanisms and dynamics of motility. And to quote from from Alex Dunn's website, she is particularly skilled at using plants to persuade people to do her bidding. So with no further ado, I'm very excited to hear Rob and Christina's talk. And their title today is A Language Whose Characters Are Triangles. I will turn the floor over to you.
Thanks. That's really super
Thank
nice.
you.
So first of all, just a little bit of explanation. So yesterday, my computer has just been dying, like spontaneously just going black, and the power button doesn't work. So I took it last week to Dyno Computers in Pasadena, and they ordered me a new keyboard and a new battery. And then yesterday I went to get it installed, and I called the guy and he said, "Oh, I wish I had good news for you, but your computer is dead." And so I panicked, in a panic, wrote Christina and asked if she'd be game to use her computer with a talk we've been developing. Anyway, so it's a great privilege to be here, and just by word of introduction. So Christina and I are almost done with a really fun book that's been a labor of love for us that was started in the Marine Biological Laboratory physiology course. The book is entitled The Restless Cell, and it's basically about active matter. And that's kind of a dress rehearsal for the third edition of this book that she's also an author with us on, called Physical Biology of the Cell. And then finally, I see Wallace is here, and this is kind of crazy, but he and Thomas Lequi and I are working on a book on shape. And what we're going to talk about today is quite relevant to that theme as well. So without any further ado, again, thanks for your patience. I hope you're not too frustrated at the change of scheme, but I'm so grateful that Christina saved my ass. So anyway, so our talk is entitled Language Whose Characters Are Triangles, and that will become very clear in a few minutes what that's all about.
Great. Thanks, Rob. All right. So we'll start by saying that one way maybe we can think about grandly the progress of science is as actually a forward march of mysteries that fascinate individuals, that individuals solve mystery by mystery. And the theme, the mystery that will serve as a theme for our talk today is the beautiful collective motion of fish or birds or sheep that you see on this slide. Of course, not only big animals can show collective motion. On the bottom, you're seeing flows of molecules, actin and myosin, inside a developing C. elegans embryo. So we can ask, how can we understand mysteries in the living world like this? Like if I gave you a bunch of sheep robots and asked you to program them to recreate a herd, where would you even start? What language, what concepts would you draw on? And in our talk today, we'll start by, in part one, briefly arguing that math is the right language for this, that math is the most powerful language maybe we can engage in to explain the natural world. And then we'll move on in part two to talk about a particular perspective that we can take in this quest to understand the natural world using math. And that's the field and field theory. And finally, in part three, we'll unleash the power of the field in biology, in systems from birds to actin and parasites. So with that, Rob will take it away talking about the power of math.
Yeah, so the title, I think, is one of the most enchanting things that's actually ever been said by a scientist. So Galileo, probably many of you know, was imprisoned in his home for the last maybe 20 years of his life because he had written this book called Dialogues Concerning the Two Chief World Systems, in which he questioned the Ptolemaic hypothesis. And then when he was living in his under house arrest, he worked on mechanics, and he made this remark, which is the universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. And though, you know, I'm really a hater when it comes to undergraduate education. I'm not sympathetic to the way we teach math or physics or biology or any of it. And I think part of the problem is we always try to teach people as though they're going to become majors. If you think about it, dropping a ball or weight off of the Leaning Tower of Pisa and noting that the distance fallen in each successive interval goes like the odd integers, that is the thing that captured Galileo's imagination. He said, what the heck? how could it be, that the successive intervals are odd integers? And, really he's the one who articulated this idea that the universe is mathematical. Next slide. So I think that the figure on the right is one of the greatest figures in the history of science. It's from Newton's Principia. And what he's showing is this is the first great example of unification. What he did in this one figure is united Galileo and projectile motion and Kepler and planetary motion, noting that if you shoot a projectile off the top of a mountain, if you shoot it slowly, it will come down in a parabolic arc. But if you shoot it fast enough, it will actually fall forever in an elliptical orbit. And the thing that I think is really, really amazing, and I'm going to come back to this later, we don't have time to go into it now, but when Newton tried to prove Kepler's law that equal areas are swept out in equal times, using what amounts to modern calculus, he did it using the figure in the lower left, using the most elementary geometry you could imagine. I could show it to you in 2 minutes. It just takes two things that you already know about triangles to prove Kepler's laws. So, math reveals this unity that words cannot. Next slide.
Yeah, so this point about the effectiveness, the power of math to understand natural science is made in a beautiful and fun way by Eugene Wigner in this article entitled The Unreasonable Effectiveness of Mathematics in the Natural Sciences, which might be fun to check out if you haven't read it already. But one point that he's making here is that it's really not trivial or obvious how effective math has been at explaining phenomena that we've come up across. So maybe a simple, fun example to illustrate this is that the second derivative is not a common sense concept, like the idea of acceleration, let's say. That the math of that is really not something that we would think of or talk about in English in common sense. And so this idea that force is related to the second derivative of position, it's kind of worth wondering at that connection, which is not trivial, between a math concept and something in our natural world. So with that little vignette, maybe we've tried to convince you that math is powerful when thinking about the natural world. And in this next part, we'll talk about a particular perspective we can take, the field or field theory. I think many of you will actually be familiar with the concept of the field, even if you haven't quite thought about it that way. Maybe you've seen, for example, a map like this gorgeous one of wind patterns on the surface of the Earth. And here we're not keeping track of every gas atom. We're seeing a velocity field that's representing the wind as a field on this surface.
Something that I find really interesting is there's a great book that was written by Albert Einstein and his assistant, Leopold Infeld, who was this Polish guy. It's a great book to this day. I just reread it last year. It's called The Evolution of Physics. And in it, you hear Einstein really, really over the top expressing his admiration for Maxwell. And what he says is a new concept appears in physics, the most important invention since Newton's time, the field. And I wish we had time to elaborate on that, but action at a distance, there's an amazing letter from Newton to a guy named Bentley. And in it, he says the notion of action at a distance is so absurd as to barely be believable. In other words, how could the Earth here and the moon over there be talking to each other? And in a way, what Einstein was saying is this field concept is really incredibly potent. So what Christina and I are very amused by is the idea that we think this is really, really something hyper important for modern biology. And indeed, it goes back to Dave's comment at the beginning about phenomenological theories.
Yeah.
Okay, so there's some words that are put into play when thinking about turning molecular pictures into field representations. And my favorite way to think of about it is either with respect to something like the Golden Gate Bridge. You would never, ever, if you were in your right mind, talk about the Golden Gate Bridge as a collection of iron atoms, unless you were worried about painting it because of rust and corrosion. But otherwise, you would think of it as an elastic structure. You would note that in the middle of the bridge, there are these little grids that represent the capacity of the material to actually expand and contract depending upon the temperature. And so the way we would represent the bridge is through a series of fields such as the displacement field or the elastic strain. And so, if you think about chemotaxis, you might pipette in some molecules of chemoattractant like methyl aspartate. And instead of representing it as a series of discrete molecules, we would represent it as a concentration field. What Christina and I are showing you on the right is a collection. The columns are 3 different versions of fields: density, orientation field, and velocity. And then the rows correspond to 3 different length scales: molecules, cells, and organisms. And I don't know which figure is Christina's favorite, but mine is the lower right. If you look carefully, you might recognize that as the way that whales actually collect and do these really weird vortex patterns in order to do their eating. And then at the bottom, we show you the continuum representations of these things. Next slide. So, what is a field? The way I want you to think of it is really already shown in that map that Christina showed a minute ago, which is that at every point in space, there is a number or a vector or a tensor that tells us what's happening. So the first row here, we're all very used to the notion of a temperature field. If I get in a plane in Los Angeles and I fly to New York in winter, I may have shorts on when I start, but I need to put on a coat when I get to New York. There's pressure. We know about that when we get in an airplane, because when we're up high, we see that our water bottle actually will, if we drink and then close it, and when we descend, the water bottle will get crushed. So pressure is a field. At every point, there's a different value of the pressure, and that's the reason we have R and T, and so on. Concentration, height, velocity, and displacement and flux are vector fields, in the sense that you need 3 numbers at each point in space. And there's even more complicated examples, such as the strain tensor, in which you need 9 numbers. Or if you're more subtle about it, you need 6 numbers at each point in space. Next slide. So once we've identified the fields, the next thing we want to do is we want to write down what we're going to call a field theory. And actually, I think most of you are already used to this. So a classic example is the field theory of diffusion. On the left, if you imagine an experiment in which you have some chemokine, and then at t=0, you release a barrier, and now the chemokine can diffuse. What we're interested in our field theory setting is to figure out the space-time evolution of that field. And the way I think of it is as an update rule. If you, at the bottom on the lower left, you'll see the concentration at position X at time t plus delta t, which is the time now. Well, that's equal to the concentration a moment before, C of X and T, and then plus all the ways of changing the amount of concentration in the box I'm currently sitting in. Well, what could happen? The 4 pictures at the top show you what could happen. I could be a molecule that jumps from X plus A into box X. I could be a molecule that's at X minus A and I jump into box X. Or if I'm in box X, I can jump to the right or jump to the left. All 4 of those eventualities are captured in this K delta T thing at the bottom where the arrow is pointing. So this is an update rule. It's exactly what you might think it is. It's accounting. That's all it is. Next slide. So once you have this accounting rule, then you can do very interesting things, such as solve boundary value problems. So for example, you might start out, as we showed you before, with a concentration gradient. And over time, what will happen is that the concentration will evolve. It will change. Initially, it's the blue curve, and in the long time limit, it's the green curve, in which the concentration is uniformly distributed, but now it's half the original value because that's been diluted over the entire box. Next slide.
Okay, so now that Rob has given that fun introduction to the field and field theory, we're going to try to build our own little field theory today. And the example we'll start with is a field theory that describes flocking animals, like those on our very first slide. This kind of flocking theory was very much pioneered by Yuhai Tu and John Toner. And we'll be drawing on a minimal version of their field theory to start off our explanation today. But I'll start by maybe posing a question for you all to think on for just a few seconds, which is, if I were watching a flock of starlings flying over Rome, and I were talking to a Pixar animator, let's say on the phone, and I were trying to give a description of that flock so that the animator could recreate it, what field variables might I use to describe the flock? Maybe just think on that for a couple seconds. Okay, so the ones we're using today are the density field, which is a scalar, the number of birds per box over here versus over here versus over here, and the velocity field, vector field that says, let's say birds over here are flying slow, birds over here are flying fast, for example. And then what we want to do is to figure out the update rules for these two fields. So how can we come up with rules like the ones Rob was just discussing that will tell us how our velocity field changes over time and space, and how our density field changes over time and space? This is just a kind of playful toy illustration to show you. You might, if you were trying to create a little simulation of this, maybe you'd think, okay, I start with my birds randomly oriented. These black arrows would be the velocity vectors, the direction the bird is pointing and flying. How are those birds going to evolve over time? What update rules would I want to use to evolve them? So here I'm going to walk you through one term that we have in our theory more carefully. So this is one where birds might check what their neighbors are doing in order to adjust their velocities. So they might want to know the birds next to me, the birds ahead of me, what velocities are they flying at? What should I adjust to match them? And this is something we'd hypothesize that birds would do, hypothesize their psychology based on, say, our observations of birds flying around. Hopefully you all would agree that this is reasonable. So we can say that this bird number 2, which has velocity 2, it might look at the bird behind it and the bird in front of it. And if it looks at the bird behind it and compares its speed, its velocity to that bird's velocity, it's going to say, maybe I should make an adjustment that looks like this, which is that bird's velocity minus mine. But if it looks at the bird ahead of it, B3, it's going to say, maybe I should make an adjustment that looks like this to speed up and match this bird. Then it's going to average those two velocities to get this green arrow, which is the second derivative of velocity. And this green arrow is what it's going to use to adjust its own velocity in order to democratically match its neighbors. So we can write that as the speed now is equal to the speed of the bird before, plus this update. This is this green arrow, and this is a coefficient scaling it. We can also write that in a different notation, which we'll be using throughout the rest of the talk, which is a partial differential equation where we're describing how the velocity field is changing over time. And in that case, the term we just talked about will look like this one.
So I think, just as an amusing aside, it's fun to think of the term that Christina just introduced, the smoothing term. It uses this mathematical operation called the Laplacian, but we just kind of gave you an argument that you can think of that as a democratic sort of scheme where you average the differences between you and your neighbors. So the Toner 2 theory in minimal form involves the 4 terms that we show you here. So let me just say again what the idea is. On the left-hand side, we're demanding an update. We want to know how the velocity now is related to the velocity before. And what we know is on the right-hand side, there's all these different terms. There's different, if you like, driving forces that adjust the velocity based on its current value and here and in the neighborhood. So the first term on the right-hand side is very interesting. What it says is there's a preferred speed. Birds or myosin and actin will travel at a certain average speed, which is related to the parameters alpha and beta. There's a pressure term, and the pressure term is, if you ever have a chance to watch sea lions on a beach, or alternatively seagulls that are parked on the beach, you'll notice, I've really studied this a lot, they have a characteristic mean spacing. They do not want to get closer than a certain value, but they also don't want to get farther apart than a certain value. So you can think of that as there being a pressure. There's an equilibrium spacing, and the pressure term punishes incorrect density, if you like. The smoothing term Christina just told you about. And then finally, there's this advection term, which, if you know the Navier-Stokes equations, should sort of look familiar. The 4 figures are just a schematic way of trying to represent what these 4 terms will do and how they alter the update. So we basically, as Christina said a minute ago, we have an equation for the velocity, but we also have one for the density. This one, for the moment, is traditionally known as the continuity equation. And once again, for me, lots of field theories are about nothing more than accounting. You build boxes, you ask how much stuff comes in, how much stuff comes out. that corresponds to the so-called continuity equation on the right. I think one of the most clever things that, that Christina's done in the context of using this flocking theory for, as you're going to see in a little while, for actomyosin, is the realization that you need to actually account for the fact that although in a herd of wildebeest or in a flock of birds, the birds are not dying and being born on the time scale of the flock or the wildebeest herd doing what they're doing, in terms of actin moving, the flock members are dying and being born on that same time scale. So that requires this equation to be adjusted a little bit. And you'll see that in a little bit.
Okay, so as kind of a playful, fun finale to this little section where we're trying to introduce flocking field theory, we'll try actually solving this theory that we've built numerically. So we can do that by building this kind of fun geometry, which is meant to resemble birds over a wave. And let's say now we represent our velocity field, again, as these black arrows, and we start off these velocities representing birds pointed in all sorts of random directions. And now we're going to numerically solve these equations we just talked about. And so those are going to update our field. And you'll see in this example that the birds might start to align a little bit locally with their neighbors. They might sometimes reach high densities that then get dispersed because of that pressure term. And eventually they may end up with their field looking something like this, where the birds are roughly flying in one end of this section of air, let's call it, and out the other, kind of aligned the way a flock would be. So that's all fun to see. Hopefully in this section, we've been able to give you a sense of what building a field theory feels like.
Yeah, so I guess now what we're going to do is we're going to try and use this field theory that was constructed by Toner and Tu. And in fact, many people consider the simulations of Vicek and then the corresponding analytic work of Toner and Tu to be the birth of modern active matter theory. Something in the mid-1990s. We just passed the 25th anniversary. One of my favorite things, and I think one of the most useful things for thinking about the life sciences, is the surprising relatedness of apparently disparate phenomena. Now, what I mean by that is that, the first time you learn about mass spring systems, at least for me, first of all, I thought they were incredibly boring, but I never in a million years would have been smart enough to realize that they would tell me something about an RLC circuit. Never. I would not have realized that in any way, shape, or form. But in fact, I think we all have to be honest. Though hundreds of years ago, the people that worked on masses and springs and the people that worked on electric circuits they weren't working on the same thing. But now it's completely reasonable to teach those as the same topic. And that's a biology I look forward to, like a biology of the future where we talk about ligand-gated ion channels and hemoglobin in the same breath because they're allosteric proteins. So what I'm excited about now is we're going to completely shift off of this length scale, and we're going to talk about toxoplasma and actomyosin. Okay.
Okay, so on to part 3. How's everybody doing?
I'm nervous. Thanks for asking.
Yeah, I'm right there with you.
All right.
So as Rob was previewing, in part 3, we'll be still using our basic flocking field theory, but we'll actually move from talking about birds to talking about a different biological system. And
yeah, I suppose maybe I forgot. This is very spontaneous, so we're trying to get our act together as far as who's going to say what. But I think I have 2 points that I'd like to make about this particular slide. So I kind of already made the point, but I want to say it, I think, more dramatically, which is, isn't it wild that the same field theory can be used to describe phenomena that are more than 10 to the 9th orders of magnitude difference in length scale. So, on the left, we already saw that's whale and krill and all that stuff. And on the right-hand side, we're talking about, the local organization microtubules or actin or something like that. The other thing I wanted to say is that this is, from here on, what we're about to tell you is really preliminary work. So again, I'm very grateful to Christina for being game on the 11th hour to just come and save me when my computer has died and I didn't have a talk ready. But we're very much looking forward to feedback. But we're still in what I would call the hypothesis mode, and she's still doing experiments and so on. So I guess I just wanted to put that proviso up.
Thanks, Rob. Yeah, maybe the last thing I'll just explicitly point out here is it's pretty fun that these krill and these cells and this actin, their movement at this point in time can all be described with the exact same math. So these same velocity fields. And we were just talking about birds and their collective motion. And if we look at this eukaryotic tree of life, birds are way over here, but we're now going to switch all the way over to the other side of the tree of life here to talk about apicomplex and parasites and the collective motion of their actin molecules. So quite the shift in some sense, but from a mathematical perspective, there's a lot of sameness. So apicomplex and parasites, for those of you who don't know and love them, are a phylum of single-celled parasites, which includes Plasmodium, which causes malaria, Toxoplasma, which causes toxoplasmosis. You might have heard of this in the context of being told that women who are pregnant shouldn't take out cat litter. And these parasites, when they're moving through a host, so say you've ingested some toxoplasma, it's trying to get out of your intestine and to your brain, they use a unique kind of motility called gliding, which you see in this video in the top right. If you look up a textbook of how eukaryotic cells move, you might see swimming with cilia and flagella, and then crawling with lots of cell shape change, actin-rich protrusions being built and retracted. But these guys glide over surfaces, so they're attached to a substrate, but they're not changing shape at all. So the mystery we're going to start with today is how are they doing this and how are they powering this gliding motion? What we do know, I can tell you, is that we think that actin-myosin are responsible for generating a force for gliding, and that they are confined in this almost shell, very thin compartment at the surface of the cell. So there's this outer plasma membrane, which you see in orange, and then an inner membrane in gold, and those are just 25 nanometers apart. And that's where we think all this action is happening. So people have shown that most likely these myosins, specialized myosins, are anchored on the inner membrane here, and then they're gliding or they're pulling and scooting these actin filaments around within this compartment. To give you another sense of length scale, I should say these cells are about 6 microns long, so quite small compared to many of our cells. So we can think about this setup maybe actually like a traditional in vitro gliding assay where motors are anchored down on glass and then they're sliding filaments around. And that's what you see in this movie where actin filaments are gliding all over the place. You see these comet trails tracing their motion. But of course, these are moving all over the place. That would kind of be the null hypothesis in this setup. So one thing that we wondered is how are these actin filaments and their motion getting organized to create some kind of collective motion that's coherent that could then generate traction forces that would move the cell coherently in one direction. So what's the organization of actin in this context and how does it produce gliding?
So what's amusing is, if you think about it, the question earlier in the talk was, what provides the organization of wildebeest or of starlings over Rome or of fish that are swimming around? And so what we were intrigued by is there's several different kinds of theories about self-organization of microtubules and motors, or alternatively of actin filaments and their associated motors. Originally, Christina and I had a lot of fun pursuing the motion of actin in the context of the large alga called Cara. This is some beautiful work done by Ray Goldstein, Woodhouse and Goldstein. But then we were intrigued in turn by the idea of using the toner 2 theory. So for our purposes here, the key point, once again, is that we're going to keep track of density on the one hand, density of the actin filaments, and their local velocities. And so there's 2 field variables. So next slide. And the outcome of this is that we're going to essentially borrow the toner 2 theory, except now we're thinking about flocking of actin and myosin, or sorry, actin. And the equation that you see at the bottom is precisely the equation that we wrote earlier, with one exception, which is that there's now a new term on the end, which is the so-called curvature penalty. The way that I want you to think of this is the claim that an actin filament will know if it's oriented in the circumferential direction of the toxoplasma cell as opposed to the long axis. So the way I want you to think of that is that there's a free energy gain to be had, or free energy reduction and improvement, if the actin filaments align away from the direction of maximum principal curvature. So that's what this term signifies. So given this amounts to a field theory. These 2 equations tell you about the density and the velocity field, but now repurposed, instead of thinking about starlings, to think about actin.
Yeah. So to give you a sense of that, we still have a preferred speed that myosin is moving actin at. We have alignment, sort of this democratic smoothing of filaments because there are cross-linking proteins that we know cross-link filaments in this system, and because of collisions and sterics and alignment. So a lot of the same concepts and the same math from our flocking theory. But one big difference is that now we want to solve these equations on this very complex geometry, which is the surface of the cell. So it's now a curved surface living in 3D space. How are we going to solve these equations on this crazy geometry? To do this, we did 2 things. One was to obtain really high resolution tomograms of toxoplasma cell shape, and then turn them into surfaces or meshes that we could use for a numerical method, which Rob will talk about a little to approximate this really complex geometry into something where it's doable to solve our equations on it.
So I don't know, probably this is a bridge too far for many of you, but I'm just highly amused at the way that triangles have been used in the history of mathematics. And here are 2 examples that I hope you'll be pleased by. So the first one on the left is a page right out of Archimedes. You might remember that Archimedes tried to figure out the area of a circle. You know, in the classic world of geometry, people knew how to handle things with straight edges. But the moment you encountered curves, all hell broke loose. So what Archimedes did is he had this beautiful idea of pinching the area of the circle, pinching it from within and from without by first a hexagon. So draw an inscribed hexagon and a circumscribed hexagon. You can find the area of both of those easily, and you know the area of the circle is pinched between those 2 values. Archimedes did that all the way out to a 96gon, okay? He went all the way out to 96 edges on his inscribed and circumscribed polygon. That's no trivial task. And you know, he did a very good bound on pi, is the way we think of it in modern terms. But what I think we should think of really, and this was inspired by this great book called Infinite Powers by Stephen Strogatz, who's one of the great expositors of our day. He calls it the infinity principle. And what I really love about this is that he says, you know, we know how to do rectangles and triangles and things like that. And this is the sort of the history of calculus. What you do is you handle that, and then you set your triangle or your square or your rectangle smaller and smaller and smaller and smaller. This is illustrated especially well on the right-hand side. This is a page from the French translation of Newton's Principia by the Marquise du Châtelet. You need to read about her. She was one of the really great influences in mechanics. She brought Newton to the modern world by redoing his book in the French edition in calculus terms, because he did it in geometric terms. So the thing that's in green is Newton's proof of the Kepler law about equal areas being swept out in equal times. And if you look at the upper right-hand vertex of the square that I drew, you'll see what amounts to Newton's proof of the Riemann integral. No kidding. I mean, that's what's there on these 2 things. So next slide. So Christina are highly amused by this following thing. So this is also for Wallace. Maybe if somebody asked during the questions, Christina can show you. So Wallace, you'll remember many years ago that that we photo bleached the equation x² = 2dt into a keratocyte. And what Christina did here is she made a finite element mesh of that, and then we solved the diffusion equation for this very nasty geometry, and it's a quite beautiful solution. And the thing I wanted to tell you is the coupling back to this thing about triangles is the finite element method is a great numerical technique for solving boundary value problems. You know, for a while, I was kind of anti-numerics, but I've become almost like a religious proselytizer. I'm through a spherical cows, and I'm really excited about getting the geometry right. And so just for those of you that are older in the audience, you might remember in high school or junior high when we got tables of sines and cosines and things like that. One of our homework problems would be, hey, go find the value of sine 45.3 degrees. And of course, that's not in the table. So how would you get it? You do it by linear interpolation. Sorry, my dog is begging me for a toy. And if I give her the toy, she's going to make squeaking noises. So it's either I hear her or the ball squeaking. I'm going to try the ball and we'll see what happens. So anyway, so the thing about finite elements is that it's very clever because what you do is you replace a partial differential equation. All right, man, this was never bound to be an easy day. So so you basically replace the problem of finding what amounts to an infinite number of degrees of freedom, namely the density and the velocity everywhere, or the concentration everywhere, with now a finite problem in which you, yeah, this is taxing me, in which you only solve for the concentration at the vertices of these triangles. And then what you do is you solve for the values of the fields in between using interpolation. Christina, I'm gonna let you take it over so I can manage this insane dog.
Sure. So now that we've approximated our complicated geometry with this series of triangles, we're going to solve our equations at the nodes of those triangles, as Rob was saying, and interpolate between them. And here are some movies of us doing that. So we're going to start with our actin velocity field, these black arrows, randomly oriented, so disorganized. And then when I play the movie, that field will evolve according to our update rules, according to our equations. In the left movie, the color coding is density of filaments. In the right, the color coding is speed, the magnitude of velocity. So you'll see that our filaments align with each other. They start to deal with the geometry of the whole cell. You'll remember that regions of high curvature are unfavorable for the filaments to lie there, for example. They'll deal with the topology of this closed surface, and eventually they'll settle into this repeating cyclical movement of dense patches of actin going up and down the cells. Sorry that the two movies got a little out of sync. They should be synchronized. But the sort of prediction or outcome here of our field equations is that we get these dense patches that are in this kind of cyclosis phenomenon, we sometimes call it, circulating up and down the cell.
Christina, can I interject
please.
one little thing? One thing I guess I want to say to everybody that I think is so incredibly interesting is, you know, we started out with this idea about the power of mathematics, and on a closed surface like this, topology demands, it does not matter what evolution says or anything says, topology demands that there be defects. In other words, in the same way that you know, if you have hair on your head, you have to have a colic, you know? So those defects have to be there. And you can see, I mean, we could actually quantify that for you, but I just think it's a fascinating aspect of these results. Sorry.
Yeah. In other words, there's no way for all the black arrows on this cell to be aligned with each other like they could be if you just had a planar square, let's say on a piece of paper. You could have all your arrows pointing from left to right, but the topology of the cell rejects that. And that's part of what leads to these interesting behaviors. So what's fun is that we can do an experimental correlate to this where we stabilize actin. You'll remember that Rob emphasized that in the field equations we showed you so far, actin filaments are not being born and dying, they're conserved. You keep the same number of filaments you started with. So this is kind of an experimental correlate where we stabilize actin with a drug, and we see these big bundles of actin actually, and we can track those and see them recirculate up and down the cell. looking qualitatively very much like those models, which is pretty fun. We can also, though, then ask, what if we get a little bit more realistic and we acknowledge that in this system, the lifetime of an actin filament is actually on the same order as the time that it takes for a filament to cross the cell. So it's not like birds where there aren't birds being born and dying on the time scale of a flock flying around. Here we kind of have to deal with birth and death. And in fact, we know in toxoplasma that actin polymerization is favored specifically at the head of the cell, the apical end of the cell. So there are proteins there that promote actin polymerization. And we also know that actin depolymerization is important for gliding. So people have done experiments where they get rid of an important regulator of actin depolymerization. So there's less going on. And then these cells will kind of move back and forth instead of doing their usual gliding patterns. So we wanted to see how the model would be affected by putting in actin depolymerization turnover and actin polymerization at the apical cell end. And we did that by modifying our equation for the time evolution of density. So in that case, we can start with the same initial conditions, the filaments pointing all over. But if we tune our parameters in this new scheme, we can reach a very different regime in which the flow of actin is largely unidirectional. So the velocity of field stabilizes and looks something like this, in which the actin is largely flowing rearward. And this is, you can probably, there's sort of a common sense interpretation for this, which is that the filaments are dying, they're depolymerizing before they are forced back up and around. So this allows us to access this set of phenotypes or outcomes. We can also look more carefully in the model at what parts of parameter space show which of these behaviors and create a little phase diagram that looks like this, where you have actin depolymerization increasing on the x-axis. You have the amount of actin being polymerized in the apical end of the cell, the head or the conoid along this axis. And you'll see that when there's lots of actin around and not much depolymerization, then you get this cyclosis behavior, this recirculation up and down. But when there's a lot of depolymerization of actin, then you can access this unidirectional regime. And what's fun is that we think there are experimental correlates to both of these regimes from our work, but also to a larger extent from published work, work of others. And there were some confusing disparate observations of different kinds of gliding showing up in different mutants, different stages of maturity, different conditions. And we think that those might correspond to these two different regions of the phase diagram. So for example, you can see toxoplasma cells that move backwards and forwards, as you might expect for a cyclosis of actin, where that actin is getting caught on adhesions, interacting with a substrate, generating attraction force. But you also see unidirectional modes of actin motility, like on the right, like a forward, sorry, not actin motility, cell motility, forward helical gliding, twirling when the cell is up on its posterior, circular gliding, with the apical end leading. And so we're hypothesizing that these two different modes are governed by actin turnover. In other words, the addition of those new terms in the model. Another thing that's fun is we can look at these predicted unidirectional patterns and ask, well, okay, say I'm looking at this predicted velocity pattern through a glass table that the cell is gliding on. So this is the part of the cell that's in contact with the substrate, let's say the glass. Well, if actin is flowing this way, but then sometimes catching on an adhesion, which then holds the actin still, the myosin walks towards its plus end in this case, then we expect the traction force to be roughly opposite the actin polarity field. So we might expect a traction force vector that looks like this. Basically, we're saying, can we make a guess about what direction the cell would move given this actin velocity pattern? And those kinds of guesses seem like they would explain the observed gliding modes, like circular gliding, which always happens when the cell is lying on its right side, or twirling, which happens when the cell is up in its posterior, where we see a vortex in the actin velocity field in this model prediction, or helical gliding, which starts on the left side of the cell, and the cell rotates and translates and ends up on its back and then spins, ends up again on its left side. So to recap, we've used a bird flocking theory to try to understand a parasite actin motility problem, and how actin collective motion might arise in these toxoplasma cells purely due to actin interactions with itself and with myosin and the geometry of the cell. I think you're muted.
There's a really funny statement about mathematics in which somebody said, really good mathematics sees analogies between analogies. And I think what I want to say is, I don't think Christina and I, especially, I think it was 12 hours ago that she realized she might be giving this talk. We're not offering this to you as the final word on flocks or on actomyosin. We are offering it as an example of the hints that come when one, in an interdisciplinary way, tries to link up things that take place in one phenomenon with another. And again, as I said earlier, I think there are so many examples of this. Another one that I think is really fantastic is wave interference. So Thomas Young, besides deciphering the Rosetta Stone, which was actually my original title, he was a doctor first and foremost, even though he was also considered one of the great physicists of his day. But everything he did was inspired by human physiology. So he did really gross experiments on himself, on his own eyes. He worked on hearing, and he got interested in interference of waves. And so he had this epiphany where he thought to himself, well, wow, on the one hand, light is a kind of, shows interference, but sound shows interference. And then for me, my favorite example is he then was able to explain some very old observations that the British, Britannia rules the waves, had observed about what's now known as the Gulf of Tonkin. It only has one high tide and one low tide every day. It's, as somebody who's in the ocean all the time, I find that stunning. Most places have 2 high tides and 2 low tides. There's only one of each in the Gulf of Tonkin, and that was realized to be due to water wave interference. So there are oftentimes things where you might say, those are different. Why are you talking about them as though they're the same? Where the mathematics or the physics actually reveals them their sameness. So I don't know, I'm ranting too much. Let's go on. So I think this has already been said. The Galileo made this point about math as the language of the natural world. I think our next slide is an invitation for all of us to take 10 seconds just to watch something wonderful, and then I'll comment on why. Hopefully the sound works. Stop it. Mm-hmm. So in the 1890s or 1880s, Heinrich Hertz figured out if you push on an elastic surface, what the displacement fields will be. And it's actually the basis of what's now called traction force microscopy. The reason I wanted to show you this is that this is the indentation of fish by a sea lion. And we really, that's a mystery. It's something you could just watch on a beach, and or you could watch border collies with sheep. And I'm telling you that, in my opinion, we really almost know nothing about how to think about a system like that. It's just sitting there in front of our eyes. Somebody could have noticed this 2,000 years ago. And so, this kind of mystery is the kind of thing that the active matter theories that we talked about today give us the possibility of studying. Maybe we'll go for the last slide. So thanks for your patience with us for this, this last minute rearrangement. Christina and I are deeply grateful to our book co-authors shown on the left, but more importantly, she's been working in the lab of Alex Dunn and collaborating with John Boothroyd and Liav, who I think is a postdoc also in John's lab. We've had a lot of really useful discussions with Yuhai Tu and John Toner, and both Christina and I are deeply grateful for all of us are so privileged that we get to work on things that we find fascinating, and we're paid to do that, and the taxpayer money is what comes our way. So we're deeply grateful. I don't know if you want to add anything, Christina, to that.
Nope, that was great.
Okay, well, so that's our talk.
Thank you.
Thank you all for listening.
And thank you both, Christina and Rob, for a fascinating fascinating presentation. It was really cool. I loved watching it. I'll probably rewatch it a couple times, and with permission, share it with my husband because he's a math guy, and that was really cool. So thank you for that. If we could all share a little emoji love, tell everyone their thank yous.
What's an emoji?
Yeah, so you can see kind of in the screens right now, people clapping for you or sending little hearts or things like that. Because otherwise in Zoom, it always just sounds like one person clapping, and that's sad. But thank you very much for that great presentation. What we're going to do now, our participants are used to it, but just so that you know as well, we're going to move into some small group discussions where they can ask questions to you. We've been capturing those in KaiStorm. I highly recommend people continue to capture those questions. We'll take a short period of time in those breakouts to keep generating questions, and then we will come back for Q&A with Rob and Christina.
One point, I think actually Christina has to go, so I'll field them on my own, but yeah, so.
Thanks for letting us know, Rob. And thank you very much, Christina, that was great. So with that, Malachi, whenever you are ready, we will go ahead and get breakout rooms going. And Rob, you will find yourself in a room with Suzanne and Dave so that they can show you where the questions are and all of that and come up with a plan.
Great. Okay.
All right.
Care. See you later.
Time to go.
Hello, welcome back. So we are now going to turn it over to our two keynotes and Suzanne to kind of moderate our Q&A session. So I wasn't expecting to be spotlight right there. Sorry about that. So the floor is yours.
Well, I don't know how you all want to handle this. Do you have a favorite question that you'd like to start with, or do you want me to just choose one?
They can pick out the questions.
Oh, awesome.
Yeah.
I will close my mouth.
I have no idea.
Our group had a physics graduate student who had a question that I thought sounded like physics. So I think Liz can ask that question for her.
Sounds
Liz?
great.
John, why don't you ask it?
Well, no, let's have Cass answer, because it had to do with the mesh.
Yeah.
And how the size of the mesh would influence or limit the analysis, and whether you were planning on changing that as you go forward.
Go for it, Christina. You have thoughts about it. And maybe I'll share my screen in a sec after I find something.
Sure, I think in a way that's a very deep question, because it kind of gets at the difference between the ideal, like we have this field theory which exists on this infinite continuum of this curved space, and we're trying to truly solve it on that real geometry. But to actually do that, practically speaking and numerically, we're using this mesh, which is an approximation. So it's kind of like this tension between what's doable in the practicalities of the real world and what's like the ideal of the math or something like that. I think one more direct answer to the question is that we can try to do it on finer and finer meshes, which is just computationally expensive. It's just slow. And then we can compare and kind of make sure that our results aren't changing as we vary that mesh size and settle on something that we think is a good enough approximation. Did I miss something? Rob, do you want to add?
I was just going to say, I mean, one of the most amusing things, probably most of you are experimentalists, and one of the things that we so emphasize in the lab is controls, but there's all sorts of interesting controls that one can do when you're doing numerics like this. And one of the things you can do is you can compare to analytic solutions. You can also compare to doing the solution, using standard PDE stuff. These are some graphs that Christina and I made that had to do with exploring things like parameter space, mesh size, time step choice, and all of that business. And like I can put it in very concrete terms. If you tried to solve the motion of the moon going around the Earth and you used a time step of 20 days, clearly the solution would be wrong. And so you'd have to bring it down to smaller, like, maybe 1 day time step would work, or maybe a half day time step, and so on. And so, those kinds of things you can see here, like this is the curve is the analytic solution that we found. And then this is COMSOL, which is a finite element technique that we've been using. And depending on whether you do a default time step or a more frequent time step, and, similar things can be said about the mesh. So it's a really great question. And, the best version of this is to do adaptive meshing. And what I mean by that is, you choose the mesh so that the refinement depends on where you are. If you think about, it's actually very amusing. Some of the most enormous computing power is used in Hollywood. And it's used, for example, if you're looking at Beauty and the Beast and you look at the Beast and the Beast is dancing, then the resolution that needs to be used on the Beast's face is different than the resolution of the mesh on the body. That should be evident. And so, adaptive meshing is really important. So hopefully we won't get too stuck in all of that, but it's really an important point. Other questions?
Yeah, there's a bunch of questions. So I will go ahead and just start asking a couple of them in order, if that sounds okay. So there is a question that says, how do you think field theory and vector spaces can be used to study stochastic processes where there is some amount of randomness involved? Or do you think that there are some problems in biology that your approach is not well suited to solve?
Well, I'm sure that there are problems that it's not well suited to solve. That's one of my shticks is that I often, like I said earlier, I don't buy the idea that you should use atoms to think about the Golden Gate Bridge. And, I'll be obnoxious and provocative and say, I dream of a biology without structures and sequences. I mean that. It's not even fake. I literally mean it. And so, but the field theory thing, let's not get carried away. There's plenty of things that it wouldn't be relevant for. And, just sickle cell is a perfect example. You make a single amino acid change and you completely change the character or the shape of red blood cells, so that's just a different world. What I would say about stochasticity is that people definitely know how to use finite elements and field theories in the context of stochastics. And in fact, there's no better example of that I know of for me. Sorry to go back to the bridge example, but I was I lived in San Francisco in 1989. I remember the very big earthquake. I was out on the highway. It was not a good day. But the thing is that it's really cool. It's actually super cool that you can do stochastic loading of a structure and figure out what its response will be, whether it will get into resonance or whatever. So including stochasticity is kind of going along the lines of what's called a Langevin equation. You put in a noise term. So I think that that's totally doable. In fact, Christina has messed around with noise in various guises in these things. So what you do is, we had that update rule. Here's the simplest way to put it. There'd be an extra term, which is noise. So you draw a random number, basically, which would perturb you off of the deterministic solution. I don't know. That's probably too long-winded.
No, I think it was great.
Great answer.
Didn't understand many of the words that you said, but I think it sounded like a really great answer.
It was just the right amount of wind.
Yeah, okay. So another question for you. The examples you've used seem to capture movement at steady state. How do you model t equals 0?
Yeah, so the t equals 0 thing. Why don't you go for it, Christina?
Sure. Maybe the simple answer that comes to mind is there's some art to it, but in our case, we've chosen to usually start with a totally disorganized initial condition. So basically, we're randomly selecting an orientation for each velocity vector. I guess the details of that, I don't know. That's interesting. We might randomly choose an angle between 0 and 2 pi for visit each vector on our field, and then randomly choose an angle and set it. But maybe another answer is that we're most interested maybe in the at least the statistical steady states that emerge. And so we don't worry a ton maybe about variability across initial conditions, but we also try to test many different initial conditions to make sure we're not seeing dramatic or seeing different effects at the end. I don't know, Rob, do you want to add to that? I'm not sure I got it.
I mean, one thing that I would say, and I'm going to actually point people to a paper. First of all, there's a paper by Woodhouse and Goldstein in PNAS called Cytoplasmic Streaming in Plant Cells Emerges Naturally by Microfilament Self-Organization. But the thing I wanted to tell you about is there's a paper from 2000. It's in a strange journal called Protoplasma. And the first author is Foisner, F-O-I-S-N-E-R. And the reason I'm telling you about it is there's this giant alga cell called Cara, and it has an organized actin cytoskeleton on its surface. And the reason I like that experiment so much is that they apply a drug which eliminates the organization, and the same structure comes back, and it's basically a barbershop. It's a helical barbershop pole sort of structure, but where, if you like, you can think of the barbershop pole as having been rotated. In other words, the structure is the same, but the initial condition will lead to where is the part of the barbershop where you go from red to white, from red to blue. That will be different, but the red and the blue won't be different. So I think that this issue of initial conditions is actually a very interesting one. There is an arbitrariness, but it's also interesting because, as in the case of Cara, it's interesting because it shows you that the self-organization doesn't care about the initial condition. It's robust against those initial conditions. Yeah. Other questions?
Yeah, so I'm not gonna lie, there's a bunch of more science questions in here too, but I'm not sure how long, Christina, you can stay. So I wanted to ask a different type of question really quickly, just in case. There was a question around how would you change teaching paradigms? So you had kind of mentioned that. So what are your thoughts?
Yeah.
I think that's a question for Rob.
I think the first thing I would say about this is that nobody should ever listen to me about anything like this, because I don't think I have any good ideas. But at the end of the day, what I was saying in our little breakout was that what I despise about the educational system, and there's real meat, there's teeth to those words, teeth to the tune of me leaving high school and not going to college, teeth to me offering our kids money to quit high school. Like I really feel this with a great passion. I think school is soul killing, and so the emphasis on grades and exams and who's going to get into Harvard and all that, it's just, to me, it's poison. So yeah, I don't really want to, I feel like it's my personal stuff and my own baggage, but for sure when I teach, I'm not interested. What I was mentioning is the last time I taught freshman biology at Caltech, I told my colleagues, I said, I refuse to talk about 5' to 3', because the moment anybody orders primers, they will discover for themselves that 5' to 3' exists and matters. And when their primers point in the wrong direction, they will learn about 5' to 3'. So how would I wouldn't change anything. I don't have a clue. I don't know what to do about unions. I don't know what to do about public education or whatever, but I will tell you this, I don't like it when I go to the doctor and every single one of them says, oh, physics was my worst class. What kind of a world makes sense in which, my dad is basically on his last legs with cancer, or he's been given a great extra life, and many of the things that have been given him came from physics. So why on earth do doctors think that physics is some sort of, an obstacle to getting their medical degree? Well, it's on us, because we teach them to become, parrots that spout off things about how much magnetic field you get with a certain number of coils in an inductor, something that's absolutely irrelevant. So anyway, yeah, this is why I should not be talking.
Do you want to talk about
soapbox?
All right. No, I don't want to be on a soapbox. I want to mind my own business, but I feel it's super.
Talk briefly about the role of wonder or curiosity. I thought that was a nice little riff you were giving in the breakout.
Yeah. Well, okay. So, these little notebooks that I have right here, they're waterproof notebooks. And they're geology notebooks. And so Victoria Orphan and I, we teach a class on evolution, and we give these to our students, and we spend, when we're with them out in the field, we spend 20 minutes of silence at least twice a day. And we always tell them to start sentences with the two words, I wonder. And I don't know, like I've been at Caltech a long time now. And what I'll tell you is that there's tons and tons and tons of people that got perfect scores on SAT and they were valedictorians. And yet, if you ask them to start a question with the word I wonder, or a sentence, or alternatively, if you say, given everybody, your parents and everyone else would leave you alone, what would you do in science? Precious few are ready to answer that. I think that's a problem.
So that sparked a follow-up question, Rob. Maybe you could talk about the class you teach in the Galapagos.
Yeah, I see that's Liz. It's so great to see you, Liz. I miss you. Liz was at Caltech actually, and was a good friend of mine, and we taught at MBL a few years together as well. Yeah, so I mean, basically my scheme, and this is one of the great privileges of Caltech, is that I keep on, asking them to give me the chance to do something other than death by PowerPoint. So, freshman biology, I think I've taught it 12 times now, which is quite a few times. And after doing it 4 times in death by PowerPoint mode, I said, could we turn this into a strictly lab class? And, the very first day of class, we go and we set the pond on fire, doing the Volta experiment where you, collect methane from the ponds at Caltech. And so, and then, I do these lab courses. So the one that Liz is referring to, I went to the provost and said, I'd really like to do a course that has a field trip. And I should point out that Harvard has such a course, Cornell has one, and there's other places that have. Yale has a really interesting thing. Again, this is for people of an enormous privilege. That said, we live in Los Angeles, and you can go to the La Brea tar pits, and that's a really, really different vibe when talking about extinction than sitting and yakking at people with PowerPoint. And so at any rate, this course culminates in a trip to the Galapagos. And the way that we came to this thing about the notebooks is my friend Ernesto, who's an Ecuadorian guide par excellence. We got off on North Seymour Island one morning, the very first morning of the trip. All these great students from Caltech were clicking their cameras like mad. And Ernesto said, God damn it, that's it. I want all of you to sit down right now, put your cameras and phones away, and shut up for the next 25 minutes. I don't want to hear one peep out of a single one of you. And what was really interesting is that the students begged for us to do that. So we would do it 2 or 3 times a day. And we've been, and then we give them these notebooks, and that's pretty interesting. Probably the most compelling time that ever happened was in New Zealand. We were in the fjords, and I had 50 students, and it was 10 p.m. It was getting to be sunset. We were out in the ocean. And I got them all to sit in silence. There actually was a French couple on the ship too. And everybody was silent for nearly an hour. And at the end, the French couple came up to me and they said, that was absolutely magical. And I have no idea how you just got a bunch of 19-year-olds to be quiet for an hour straight, while looking at the fjords and trying to think about evolution. Anyway, I don't know. So the bottom line, Liz, to be perfectly honest, yeah, I do teach these classes, but I don't think I have anything to offer like as a generic thing. As I was told at HHMI, I probably shouldn't say this, but they said, we get it, you're charismatic, but we need to reach 10,000 people, and I don't have a clue.
Okay, so in our last few minutes, we have a few more questions. I want to kind of head back into the science realm for you.
Yes.
So there's a question, and please, if there's one where you're like, I addressed it past, just let me know, because there are quite a few. So do you think that field theory and field variables can be helpful for studying molecular condensates and the regulation of liquid-liquid phase separation in biology?
Yeah, for sure. I mean, they already are. I don't know, you want to have a go at that, Christina? It's kind of fun. I mean, you've thought about it a lot.
Oh, sure. Well, maybe the short answer is I think yes. And I think a number of the theories that people have drawn from the equilibrium world and applied to understand these transitions between different phases and to build, phase diagrams you might be used to looking at, those are in fact field theories in which we're not keeping track of every single molecule of protein A and protein B that are phase separating, let's say. We're understanding them as concentration fields.
Yeah,
I'm sure Rob has much more to add.
No, but the Florey-Huggins theory, and there's phase field models and stuff. So what I would say is I would go farther than the question asker. I would say that is the proper description. You know, in other words, if when I teach it, for sure, I don't talk about the individual molecules. I might if I want to talk about the parameters in the field theory, but the language for me is field theory. It's not molecules.
Yeah, maybe that's a nice point to make. Like you might, maybe you noticed in a number of the terms in our field theories, there'd be some coefficient, you know, at the front, some parameter, and thinking about the molecules in your phase separating system or whatever might be important for figuring out those parameters, like thinking about the molecular properties, I guess is what Rob is pointing out. But then those molecular properties might enter into that coefficient and stay there.
That's right. Yeah.
Okay, I think we have time for one more question if you're up for it. So regarding the actin field equations, how would one consider the changes in the toxoplasma surface change over time as well, as it is not a static figure?
Oh, I'm so glad someone asked that, because it makes me realize I did not point out an important thing, which is that these toxoplasma cell shapes are actually very stereotyped and very static. So at least on the scale of the lifetime of this life stage, there's this rigid cage of microtubules under the surface. This is very different than like we've seen movies of a crawling human neutrophil or something that's just doing these gorgeous, insane shape changes as it crawls along. These cells, part of what's mysterious is they maintain their shape. It's not changing. So it's reasonable for us to have a mesh that doesn't deform. And they keep that shape as they glide along. So it's kind of like a rigid banana yam shape gliding forwards.
But maybe you can mention your thoughts about other organisms that you have thought about where you are going to look at shape change, because I think it is really amusing.
Yeah, I mean, I guess personally, I'm excited about understanding how to keep track of. That's kind of like a next step in terms of my education and such, is to think about in cases where there is, let's say there's another parasite that is a super fun one, Schistosoma, which has these dramatic changes in shape and size and body plan during life stage transitions. A lot of parasitic organisms go through these crazy changes in form because they go through such crazy changes in environment. Like they're free swimming in a pond, but then they find a human and they burrow into its skin, and suddenly the temperature has changed. There's immune cells that they have to deal with and run from, and they have to tunnel through tissue. They completely change shape, and thinking about those kinds of shape changes and actually then very much focusing on the changing of the mesh over time, that's super interesting as well.
So just maybe one last comment about that is, Christina and I have indeed written down the field equations, as have others. You know, we didn't mention it, but doing these theories on curved surfaces is super hard. It's very, very tricky. And so currently we're doing everything in plane, but what happens is you get an equation of motion for out of plane as well. So that's the real answer. In other words, the equations that we showed you, the V's were V parallel meaning parallel to the surface. Now you have to have a V perp. And we know how to write those down. It's doable. You get terms that relate to the curvature. In other words, there's literally forces due to curvature and stuff, which some of you work on membranes might already be used to. Yeah, so it's a really beautiful topic. Really, really beautiful.
Dave, I see that you unmuted and you're hanging out. I was wondering in the last few minutes if there was something that...
No, I'm just waiting to talk to these guys in the wrap up.
Oh.
Just being ready for that, because we really only have fewer minutes.
We do.
Pretty much at the end.
So I was actually just going to say thank you so much, Rob and Christina, again. Thank you. That was wonderful. If we didn't get your questions answered, we will work with Rob and Christina to see if we can get answers to those questions for you. And with that, Dave, I think you said you wanted to say a few words.
No, I'm just waiting to talk to Rob and Christina.
Oh, okay. Well, with that, so the plan right now is that we will currently go on our short break. or our lunch break, or late coffee brunch break, however that works for you. And if you could please be back here at 20 past the hour for our social activity, we will see you soon. Otherwise, thank you so much, Christina and Rob.